This is Math 204. Complex variables, and today we're going to, in this video I'm talking about section 2.2 in the notes, which is limits. They work in a similar way to limits in the real plane, except of course instead of the real numbers having one dimension, they work the same way as functions of real numbers, not in the real plane, except instead of having one dimension for limits, we've now got two dimensions for limits. But the concepts behind the definitions is exactly the same. Definition: f, a function of complex variables. Right, and a and l inside the complex numbers. Then f of z limits to L as Z limits to A, written f of Z goes to L as Z goes to A, or the limit Z goes to A of f of Z equals L. And sometimes where it's clear from context, this portion might be left out, so you'll just see the limit. If for all epsilon greater than 0 there exists delta greater than 0, and both of these are real, so that if z is delta close to a and not equal to a, then f of z is epsilon close to L. And note this is the punctured disk, because we exclude it being equal to 0. Let me just rewrite that out. So you can rewrite this in terms of neighborhoods, and I suggest you do that. It's an interesting exercise that's well worthwhile. Okay, now there are some examples which I think we do need to show you. They're a little obvious. So I'm going to say I'm going to have a function which I'm going to denote by the number 1, and that function takes an element of the complex plane z and spits out the number. And I'm going to write down a function which I'll call I, which takes z and spits out z. So my claim is that both of these have appropriate limits. So let A be in the complex plane. Okay. Right, now, my claim is, first claim, that the limit as z goes to A of the function that always returns 1 when you plug in z is equal to 1, which is kind of makes sense. So let epsilon be greater than 0, and choose any delta greater than 0. Then we have z less than, then assume z minus the number 1, because that's what I'm trying to prove the limit is less than delta, and I picked any delta here, so z could basically be any number. Then the function that returns 1 applied to z minus the number 1 is equal to 1 minus 1, which is equal to 0, which is equal to 0, which is certainly less than delta, less than epsilon, so proven. And I understand your frustration. Maybe it's a little trivial somehow, or obvious, or something. Let's do it for the other case. So we'll take A and C, take epsilon greater than 0 and choose delta equal to epsilon greater than 0, which is a fine choice. Assume we have z minus, z minus a is less than delta. So we need to show that I z minus a is less than epsilon. So I of z minus a is equal to z minus a, which we know is less than delta, which is equal to epsilon. So we know that I of z converges to z, well, say a, as z converges to a. Great. This is the identity function. And this letter here is called iota. Okay, now, given those examples, let's go back to the definition, just have another look at things. So we have some delta neighborhood, and we say z minus a is in the delta neighborhood of 0, and f has to map that into some delta neighborhood of 0. So we have some delta neighborhood of 0, and f has to map the delta neighborhood of 0 into the epsilon neighborhood of 0. And remember, this is a punctured disk, so 0 is not actually in that neighborhood. Here's an example which I think is more interesting than both of those, and I'm going to give an awkward long proof, and in a little bit you will see a less awkward, less long proof. So my claim is that the limit as z goes to a of z squared is equal to a squared. Seems reasonable. Choose epsilon greater than 0, let delta be greater than 0, such that, and I worked this out before class. So there's some expression which is a bit magic that I came up with before class, and I messed around with the algebra to make sure I could figure out how it works. Okay, assume that z minus a is less than delta. We need to show that z squared minus a squared is less than epsilon. Okay. Now, z squared, so z squared minus a squared is equal to z squared minus za plus za minus a squared, which is equal to z times z minus a plus a times z minus a, which is less than or equal to z minus a plus a z minus a. So z minus a is less than delta, so that's good. We know delta is less than epsilon. Great. And I have an a in here, and that's the thing that I knew beforehand that we're taking the limit of, and so I'm allowed to pick my my delta thinking about the a. And so I need to control this somehow. So recall that the absolute value of the difference in absolute values between two complex numbers is less than the modulus of the difference of the numbers. So another way to write this out is that minus a plus z minus a is less than or equal to z, which is less than or equal to a plus z minus a, and that is of course less than or equal to a plus delta. So z squared minus a squared, let's put this together. There's my z, I have this bound on it, so that's a plus delta, and there's a z minus a, which I know is less than delta, plus a, and there's a delta, and that is equal to 2 lots of a delta plus delta squared, which is less than epsilon. So it's true. Right, a bit more awkward, requires a bit more thought. That did take me a bit of time to figure out. It's always very easy to present maths once you've worked it out beforehand, and if you didn't follow along with that, I suggest you work it out, because working it out will prove it for you. So now some more definitions. The limit as z goes to infinity of f of z equals L if for all epsilon greater than 0 there exists a k greater than 0, so that if z is greater than k, then that implies that f of z minus L is less than epsilon. You can draw a diagram for this. Here's my k radius thing. Here's everything outside. Anything with modulus bigger than that gets mapped by f. There's L, and gets put inside. Z goes to a. The limit of z is equal to infinity if for all k greater than 0 there is a delta greater than 0, so that if you're in delta of each other, then modulus of fz is as big as you like. A is my neighborhood, is mapped by f. There's k, and you end up outside. And there's one less definition that's needed, but I want you to work through the details for this. The limit as z goes to infinity of f of z equals infinity. I do really want you to do this. You write the definition down. It will help you think it through. Right. Now, essentially, because of properties to do with the modulus, we have this nice lemma, which I'm going to be referring to probably at some point in the future. So I'm going to put the number down. Right. So we've got two functions, a complex variable, and we have a and l in C, then and a bunch of statements. The limit as z goes to a of lambda times the f of z is lambda times the limit as z goes to a of f of z. 2. The limit as z goes to a of f of z plus g of z is equal to, well, it's the sum of the individual limits. Not so surprising. Just like real numbers. Same thing goes for the product. And the limit as z goes to a of f of z over g of z is equal to the ratio of the limits, but there's a condition on it. Provided that no division by 0 is involved. That's going to be a theme that you'll see coming up. So how does the proof work for this? The proof I'm going to leave to you, and I think it's a very valuable exercise to go through. The proof relies on these kinds of properties. That the modulus of the sum is less than or equal to the sum of the moduluses, and that the modulus of the product is equal to the product of the moduli. So with those kinds of properties, you should be able to work it through and prove that previous result. As an example, I will do a little one for you. This is another lemma. The limit as z goes to a of f, a function of a complex variable, f of z equals L, is equivalent to, or implies, and is implied by, that I've got complex conjugation involved, and the proof is very easy and relies on these kinds of properties, right? Because of recall. Okay. Let epsilon be greater than 0. Well, now let me say first that implies that there exists that implies that for all epsilon greater than 0 there exists a delta greater than 0, so that implies that for all epsilon greater than 0 there exists a delta greater than 0, so that implies since z minus w is equal to z bar minus w bar. Right, and this statement is the same as saying that the limit as z goes to a of the complex conjugate. And to prove the other direction, you could of course do everything in reverse, but it's a little easier to rely on the fact that the complex conjugate of is the number itself, so you can go backwards that way. And this must be page 6. There's another result which is very useful, and it's worthwhile just thinking about this a little bit. So we can write f of z as w. So this is f of x plus iy is equal to u plus iv. U and v depend upon x and y, so we can write this down as u xy plus I v xy. So if of course u and v are real, and it would be nice to interpret these kinds of limits rather than thinking of these as functions of complex on the complex plane, as thinking them as functions in the real numbers. So this is heuristic only. Heuristic, except I've spelled it wrong. You can think, I mean, this is certainly what's going on, but you need to reinterpret these. This is a function of the plane, not a function of z. So just be aware. But in any case, this bit here is absolutely true, and that's the consequence of lemma 2.2.9 in the book. Proof, a little bit of an exercise, but you will need to know about limits in the real case. So So you need to know both of these things to be able to conclude that that is true. Going back. Let me write it out, just to be clear. Limit z goes to a, f of z equals L is equivalent to saying the two statements that the limit as z goes to a of the real part of f of z is equal to the real part of L, and the limit as z goes to a of the imaginary part of f of z is equal to the imaginary part of L. Again, proof left as an exercise. You need to know both of these in order to be able to conclude that. Not too complicated. Take the bounds on both bits and add them together. It's worth noting that the same doesn't hold for the modulus, because of course the same complex numbers have the same modulus. Lastly, definition. A function f is continuous at a in the complex numbers if the limit as z goes to a of f of z is equal to f of a, which we didn't know before. F is continuous if it is continuous at a in the complex numbers for all a. Example. Do you remember I showed that the limit as z goes to a of z squared is equal to a squared? That implies that the function that takes z and spits out z squared is continuous. Lemma. And this is very, very similar to the previous lemma we had about operations on limits. Continuous. So if f and g are complex functions that are continuous, then f plus g is continuous. Continuous at a is continuous at a. F times g is continuous at a. F divided by g is continuous at a, provided that, of course, that g of a is not equal to 0. The real part of f is continuous at a. The imaginary part of f is continuous at a. And the modulus of f is continuous at a. Proof, you do it yourself. Again, just as valuable as the example for limits. It will help you learn these definitions and work with them. Cheers.